Everyone. My name is Jackie Petrie from the National Renewable Energy Laboratory. Thanks for joining today's presentation on scalable deposition and in situ characterization of perovskites and open access R&D resources at the Washington Clean Energy Test Beds. Just to give you all a brief introduction to the platform, we're using WebEx today. We're going to have a Q&A session at the end of the presentation, so if you have any questions, feel free to submit those throughout the presentation. We'll get to as many as we can at the end. You can submit questions by using the Q&A panel at the bottom, should be the bottom right-hand corner of your screen. Note that there's both a chat and a Q&A feature, and we're going to ask that you submit questions in the Q&A panel just so we don't miss anything. We'll also monitor the chat, but we try to keep that more for technical difficulties and audio issues. So just a note to let you know you can submit questions at the presentation, and we will get to those at the end. With that, I'm going to hand things over to Joe Barry of the National Renewable Energy Lab. Joe?
Thank you very much, Jackie. It's a real pleasure today to introduce Devin McInnes, who is one of our kind of founding members for USMAP and is on our executive board and has been integral in kind of interfacing and interacting with all of our industrial advisory board members. I had a chance to meet Devin out at the Clean Energy Test Bed a few years ago, which is a really fabulous facility that he's going to be telling you more about. But without further ado, I'll go ahead and hand it over to him so he can tell you about all the wonderful stuff they're doing. Devin.
Good afternoon. So we'll have a whirlwind tour today of some of the activity. We'll have a bit of you'll get to hear a bit about what the rest of the field everyone thinks about in situ monitoring for enabling perovskite manufacturing. And we'll also talk about some other applications of perovskites we're working on and the resources available to everyone here, open access at the Washington Clean Energy Test Beds. Great. And so this fits in, our work in solar actually fits into our broader picture, all about sustainable manufacturing of optoelectronic sensors and energy devices. And even on this slide, in this broad base, 3 of these categories in solar, printed photonics, quantum materials, and in piezoelectrics, we're all seeing these new variants of new hybrid perovskites really coming to the fore. And of course, the reason we're all here is the really exceptional semiconductor performance coupled with processability. And I think that's why we're all here. And this is one vision of our ultra-roll perovskite flow, kind of shows you our vision. It's not the only one, but it's kind of exemplary. And in fact, we don't just do roll-to-roll. We do sheet-based processing as well, and so we have many users in the lab and researchers in my group and outside that work on sheet-based versus roll-to-roll. So this is not a soapbox to sell everyone on roll-to-roll, and I think most of the insights here could be applicable to sheet-based processing and even other technologies. And so we'll talk a little bit about the overall roll-to-roll, the key elements for roll-to-roll, and they're really simple, which is really, it's all about the substrates. It's inks and paper, and actually I think the inks, we got to worry about lifetime, but the inks, the printing part, the fluid part is actually, although it makes the best pictures, is actually not what I lose sleep over. What I lose sleep over is substrates, cost of substrates, substrate integration, transparent conductors. Then I'll talk about the in situ characterization work we're doing as part of a Department of Energy funded project. We're just wrapping up. And then think about some other applications for solution processed hybrid perovskites and go on and talk about our lab. So kind of overall summary, I think I've shown this before to the audience, but this is, strengths. The biggest strengths to me, and I know we're discussing this internally in the USMAP, thinking about writing this stuff up, is it's about low capital cost barrier. That's, to me, the single biggest barrier to broader adoption of solar, to get solar to be not a few percent of our energy needs, but to be 50% of our energy needs. It's not about another 0.1, 0.2% PCE. It's about reducing the $1 trillion cost barrier it would take to install the manufacturing to actually produce enough solar to supply a significant fraction of our energy needs. And that's where I really think the attack's interesting. I don't want to just invent another CAD Telluride. You know, we want to go somewhere different. And the thing that brought me into this was ultra low capital investments to get to really high throughput manufacturing. And of course, roll-to-roll is also inherently flexible. At first, that can be a yoke because it's a challenge, but it can also be actually fundamentally enabling. And that ties in really with the substrate. The challenge is substrates and encapsulation solutions is what a lot of us are thinking about, of course, because of lifetime is an open question. But in roll-to-roll, we have additional constraints we want to think about. But I really think this is, I think many of us share this idea that this is a real opportunity for domestic manufacturing of PV. It's unclear whether silicon solar cells will come back, ever come back. I tend to not think so. But here we have an opportunity, considering the very, very low capital cost, a really a workforce need that is not based on low cost, low skill labor, but it's really based on very, very high precision process engineering, small footprints, can be dispersed in manufacturing. It doesn't have to be centralized. I think that's a real opportunity for domestic manufacturing, and another reason why we're here looking at this. So first I want to talk about barrier film. So my background, I spent 15 years in industry before becoming a white-haired academic, and I started I started about 10 companies. I successfully started about 5, got them through the Series A and beyond, and various levels from plumber to CEO and CTO. But multiple of those are in displays and OLEDs world. And I spent a lot of time working on flexible barrier films, looking at flexible barrier films for flexible OLEDs. And it's a very challenging picture. This shows the water. This is a lot of the amount of water molecules per micron squared, 10 years entering from different barrier films. We want a 10-year lifetime. I think that micron. If you're a pessimist, you're going to say that long-term having a water molecule, or maybe oxygen molecule as well, within a carrier diffusion length squared is going to ultimately be, maybe it's another way of saying the long carrier diffusion lengths of perovskites and their exceptional semiconductor performance could also make them more susceptible to degradation, because in OPV, the excitons never moved more than 10, 20 nanometers in their life. So if there was no defect in that neighborhood, you might avoid it. Now we have perovskites, we have electrons, wave functions out over maybe microns, maybe even hundreds of microns, which means that they can also interact with defects in a much larger scale. So if we look at that like kind of pessimistic view, it can be challenging. We're talking about even the multi-layer barrier films. So 10 squared, kind of world-class multi-layer, inorganic, organic multi-layers on plastic, on a polyester, for lead. Even we're talking about 10 to the 7, 10 to the 8 H2O molecules per micron squared after 10 years if you don't do other things. Very, very tricky. If we take another viewpoint, let's say let's take the more optimistic viewpoint that H2O degradation is only going to act locally, in the sense that we care each unit cell of the perovskite. Say we match one water molecule per unit cell of perovskite. Oh, maybe that's the very optimistic degradation limit. Like, we'll have perovskite until the stuff literally dissolves. We'll have a solar cell until it dissolves. The reality is probably somewhere in between these two extremes. But even in that case, we're getting still near one H2O molecule per unit cell in 10 years. Literally, the film will be, unless we do something different, entirely saturated with the best flexible barrier films. And then there's other stuff like what about edge seals? What do we do to improve this a bit? Gettering. Gettering, I think, is critical. Gettering is fundamental to OLEDs, and there's some real novel ways to use gettering and roll-to-roll that I've worked on, and many others have as well. But even with all that, barrier. I don't, this is not where I place my bets. I think that the real opportunity in there and is also a real opportunity in carbon footprint and energy payback time. This is from Energy Environmental Science paper. I picked this one. There's a number of life cycle analysis papers out there, different viewpoints. They really comment on the energy in where the energy comes is in they come to the TiO2 as it's a big energy result. That's also an energy and investment. But this not going to use gold. We're going to use copper, whatever. Still, cathode evaporation is a huge fraction of the manufacturing energy consumption to produce PV. And look at energy devices, the majority of it, and the majority of that is just about the glass. It's about the ITO glass. That's where all the energy is. So those are challenges, barrier properties, and this immense embedded energy related to the glass. But that opens up a real opportunity. We're talking about moving to thin glass, moving through processes. This is down as we move through, say, a progression, increasing UV, increasing bacteria, and thickness of glass. We just not because say this is low grade DC. We knock down the thickness of glass, and we massively reduce the energy investment into the whole cell. It's all about the thermal process, the amount of energy it takes to melt and process that glass. If we use 20x less of it, we got a huge chunk of invested energy. As we increase, we get better about learning better about edge shields, increase the QE, we can reduce the embedded energy investment just based on using thin substrates, thin glass substrates. There's full disclosure, I have a collaboration with Corning, but it didn't happen. They didn't show up to me and say, here's some money and some substrates. No, I chose them. I saw this is how it's going to work. My experience in OLEDs and OPV and TFT, flex TFT displays, with moisture barrier films, flex glass to me is the immense opportunity here and a real crucial opportunity. And it touches on several things. Of course, it's thin. 40 micron willow glass has a rollable diameter of 4 inches, which is quite good. Good enough for most roll-to-roll systems and most processing. It's right on the edge. And the failures are actually typically extrinsic. They're not intrinsic to the glass. It's not a limitation. It might have something to do with edge defects. It might have to do with shearing, but really extrinsic mechanism, not the fundamental flexibility of the glass per se, or robustness of the glass itself. I think it can be dealt with from an engineering perspective. Can be overcome and deal with this. Over this. Once we swallow this pill, there's some really great things. Of course, an extremely high water vapor transmission rate barrier. Permeability of water is extraordinarily low. It's really not measurable. There's really not a technique that can measure how low it is coming out of glass or say thick metal foil or something like that. It's way many orders of magnitude lower than the best we can measure, which is about 10 to the minus 6, 10 to the minus 7 grams per meter squared per day is about the best we can measure. But it also is really important because it enables high temperature transparent conductors. We take for granted when we do our spin coated samples on our little chips, we get our little FTO or ITO, and it's like 10, 20 ohms per square. That requires a 300-400 degree C deposition process. You can't do that on plastic substrates. And we'll show you how good or not so good the best ITO on plastic substrates is. So to me, plastic barrier substrates in this space is kind of dead in the water. But there's a huge win here for flex glass because not only do we enable high temperature processing, we have all the moisture barrier we could hope to get. And we're also can dramatically reduce the carbon footprint from plate glass just by the fact that it's thinner. Even if we don't roll-to-roll print it, even if we sheet coat it, we still have a real win here. And the only question mark is cost. But as far as I'm aware, there's nothing unique and different about the processing of, say, willow glass from other display grade and PV grade glass. So the pricing right now is probably recouping, trying to figure out what how to recoup research investments, kind of figure out what the market can bear. I don't see any fundamental reason why the cost of willow glass can't be actually significantly less than thicker glass ultimately. But of course, that's a question of scale. But I think we can get there. I haven't seen any reason why it can't become actually cheaper, because we're just using less glass and we're using less energy to make it. So from that, I kind of segue into our next section on in situ photophysical monitors, corrective algorithms. This is was a CEDO SIPS project. I think we started this in 17 and actually finally got started and funds going kind of 2018, 2019, just in time for a little bit of runway and then COVID. We've managed to, I think, get some interesting results out of this. And I'm going to talk first about the first stage of this, which was like a roll your eyes. Oh, we have to do stakeholder assessments. That's the new thing, right? That was the new thing at the time. Every grant, you need to do a stakeholder assessment. It grumbled. We set up to do it. Actually, it turns out to be super interesting and actually maybe one of the best outcomes of this whole project. So this is confidential names, so I'm not going to reveal who's this, but this basically stakeholder respondents represent a significant fraction of US MAP participants in all the perovskite companies in the US, almost all of them. So we're all there. Interesting thing was, just thinking about basic stuff we know are important for process environment. Interesting, the big choice was full nitrogen purge, which I thought was interesting because at the time you look in the literature and people are talking about there's this little Red Riding Hood, there's too much, too little, there's just right, and that they wanted these magic windows, but the field, personally, actually they want just full nitrogen purge in the environment, and that kind of informs how you would construct enclosure for roll-to-roll or sheet-based processing. It's important to know. And we developed an enclosure system. We've worked with we'll call an air knife, a nitrogen knife. We give the of the air knife showing the kind of circular in the box chamber locally enclosed, because we only want to have to control the humidity and temperature right near the slot die head and the flow right around the slot die head to have consistent flow. Up to full bubbler system and system, we could actually bubble water into nitrogen to get to a relative humidity. I mean, relative humidity scales are calculated for air, which of course is 20% oxygen and some other stuff and change. We made not water saturated nitrogen and mix that with dry nitrogen, feed it in at different rate, flow environment on the knife, and we really control that quite well. This kind of different flow rates we're trying to control at 10%, and within a couple 1 or 2% RH, which is about as good as you can really hope to get. We are able to control extreme excursions when the outside Seattle weather gets to 80% RH externally. But we can use we can also use kind of intermediate room control. We can put sort of rough dehumidifiers in the overall processing lab that bring it down to maybe 50% RH, 40% RH, something like that. Local box, fine tune what we want the humidity to. And this is just an example. This is offline time resolved photoluminescent signals off of slot die coated and a spin coated reference film. And interesting trends here. The trend here is there's a strong tau in the lifetime versus relative humidity, but it's characteristic that we see this dip in the middle, and actually at high humidities, we actually see long lifetimes. And then I think that's been observed by other people as well. Interesting. It's also interesting to remember that time resolved photoluminescence gives, of course, the minor carrier lifetimes, the kind of basic photophysics, but it's not the only story for making a device. So we can high lifetime, but not something that makes a very good device. And we'll talk a little bit about that in a moment. Sense the fact that we're getting lifetimes, the more we crank up the humidity, which is antithesis of where everyone wants to go in devices, and everyone's seeing the best devices at low humidity. Ultimately, a spoiler alert, it's about grain size. We can actually make huge grains at high humidity, and those really big grains can actually give quite good TRPL signal, but they can make lousy devices. But we took a stakeholder. What's the stakeholder choice on the first choice of photophysical probe? So again, the goal of this project was to develop in situ photophysical monitors to monitor growth of perovskites and feedback in an in situ continuous way. And so general strong agreement. The time resolved photoluminescence was kind of broadly accepted as quite useful. And, it's the most direct and simple but direct way of measuring sort of the optoelectronic quality of the film directly. And this is an example we built. We prototyped a PicoQuant fiber-based system. The real key for TRPL was, could we do it fast enough? Could we get enough signal? Our target was to get to a 10-second integration time. So we integrate for 10 seconds, and can we reliably measure a tau, measure a reproducible lifetime? And then, because that would enable us to then go and change feedback and change process parameters to fix, say the tau is moving too high or too low, it could actually go too high. Well, if we can get an answer in 10 seconds, we can respond in a few more tens of seconds and actually bring the process back under control before we end up printing meters and meters of garbage. We can respond quickly and feedback. And we actually showed that that's really possible with pretty simple off-the-shelf PicoQuant time harp systems, fiber-based laser delivery, relatively large area detector, but nothing super special. And we actually easily discern 30-second field, just example, but we could measure the time constants pretty accurately, even with a 10-second integration time. So pretty good, but this can't be the whole story. We can't just have TRPL. That's not enough to ensure device success. So the other aspect we already kind of insinuated is grain size. And it was no surprise. Everyone was interested in measuring a grain size. That was one of the most unanimous. And interesting that people wanted what size of grains we wanted to see. So this is kind of the percent of the voting percentage where people thought the most interesting grain size range was going to be in the 500 nanometer to micron range, with some tape. So there's definitely some people going to be using grains, though. Right, I thought it was pretty interesting. That's important because grains are, in our experience, directly related to yield. Here's a quick little video. You can see this. This is a sequence of perovskite growth at different substrate temperatures, and you can see the rate of growth increasing, and you can see the grain size going down and down as we increase that transformation. Now follows the spin coating version. Spin coating is sort of hyper quenched, really fast transformation rate. It leads to much finer grains. But the real story here is, we're growing, 50 micron grains that are relatively two-dimensional. These are not these crazy needles and things that happen like that. But ultimately, that's still a problem. If we look at topography in these three-dimensional growth, in the largest grains, and that a common failure it leads to dissolution through pinholes, attack going through the perovskite and attacking a material underneath the perovskite, leading to great big hole, or even just real micro short sort of in the device, which will sap the device efficiency. we can't arbitrarily go large in grain size, or at least I guess the holy grail is we'd like to go arbitrarily large in grain size, but only purely two-dimensionally. Can we have 100 micron grains that are exactly 300 nanometers thick with nothing bad with the grain boundaries? We're not there yet. But we think that's a real interesting area for us, because as you move to this continuous processing and slot die coding, it's a much more controlled process, a linear process, a much more controlled transformation rate. We have the ability to grow textured grains. We have the ability to grow much, much larger grains. Kind of this grain boundary problem, there's people done some novel stuff with that. TIAS, and so putting interesting things to fill in those grain boundaries and enable this large grain structure. That's a real opportunity. So that brings up the question of we need to monitor structure. Initially, we were interested in Raman because Raman was also a way to look at multi-step processes. With Raman, we could see like the intermediate phases, not just the final phase. And it was a way to probe structure that was compatible with roll-to-roll, because it didn't involve like strapping an X-ray source or something to it. We just needed a reasonably intense laser and some notch filters. But it turned out to be challenging, and actually we were able to get this is Raman spectra slide films, the literature kind of thing. So we are able to get the much more difficult. The noise is much more of an issue, because the Raman signal is relatively low until you hit it with immense powers. But the bigger problem was the variation in literature with regards to assignment of these peaks. We thought we'd identify lead iodide and intermediate peaks and perovskite peaks, but there's actually quite a bit of variation of interpretation of what's going on in the literature. And we also got, actually, it's the stakeholder choice, very few people interested in Raman. And our first choice for the second probe to complement the TRPL was angle resolved light scattering. Angle resolved light scattering is great because, well, it's kind of like a poor person's lipsometry. I mean, it's kind of in a way, but it can be very, very fast. I mean, it's elastic, so we can go sub gap so that we don't have absorption. So we don't have to worry about photo-induced degradation. We can hit it with a big laser. We can do it in parallel. We can put the detectors versus angle and collect in parallel. We can get a lot of signal pretty fast. It doesn't give as much detail, but we were looking for that signal of kind of rough grain size or gruff. Really, it's actually not even grain size we care about. We care about surface roughness related to the grains. And so we developed, this was right when COVID hit. We couldn't get into the lab. So we actually, on the way to that, developed a code to simulate the scattering profile based on. So we a really simple code. It was not to be really quantitative, but it was to show us what's the range of scattering angles where we're likely to see interesting stuff happen. And so that to inform how we're going to build our actual real in situ angle resolved scattering rig. And so we develop this, take long files out of an AF image or really any image. We use AMFF tomography images, and then actually do scattering profiles, and you can rotate that. You can sweep. You can take lung profiles anywhere in the image. We thought it was quite interesting to actually sweep the lung profiles in rotation to look for texturing. Do we see things in the linear direction of the coding or orthogonal to the direction of the coding? So that's how we developed the code. I mean, again, this is just trials, not meant to be numerical, but it shows that probably within half a radius where the actual most of the interests are happening, so we use that to refine our resolved scattering, our ARLS scattering rigs. Off with a simple prototype, we can mount a discrete photo, large area photo, because we thought we'd be starved for signal, and mount that, and we proved that worked, but have enough resolution at those low angles. So we've now moved to a linear detector system where we have a linear detector at low angles, so we can get better resolution at those low angles. And it turns out now that we've moved to like a 790, 800 nanometer laser, there's not much absorption there, and we can hit the film really quite hard. So we have plenty of signal to drive linear detector array. And so we think that's a really good coupling of TRPL to give you the photophysics, angle resolve laser scattering to give you an idea of surface topography related to devices, and both those can feed back fast. Great. So that's kind of our in situ monitoring. Now touch back on some of the other areas we work at to try to enable this. And one of them we already alluded to in glass, which is about transparent conductors, ITO. Well, for plastic substrates, I'll show you in a minute. It's basically a non-starter because the resistivity of the ITO is too high because of the temperature limitations of plastic substrates. But also we start other applications. This is a photovoltaic. This is a light panel, and then you building it. Actually has these are actually amorphous silicon. We transfer cells. Really interesting applications about tandem. Well, in tandem, of course, we actually need two transparent conductors, and we also need a transparent. There's different builds, but one of the preferred builds is there's a transparent conductor is going to go on top of a perovskite, not underneath. So then we still have that temperature problem. We're obviously not going to 300 C on top of MAPI. So interesting challenge. And here's just doing some transparent conductor loss calculations. For good transparent conductors, the loss and you take the resistive losses and the transmission losses to absorption in the ITO. But if you look at ITO on plastic, what's available, getting 10 ohms per square, and it's on 85% transmission, which is also not great. You look at that, we're talking about 30 to 40, 30, 35 total loss just from the ITO, from I squared R. That's series resistance losses in transmission. That's non-starter. So what do you do? Well, you can think about what do you do in silicon. They don't use vacuum. They don't vacuum deposit grid lines on silicon PV because we need low resistance and low shadowing, and that's hard to do. We need to grow vertically to get more metal in a small footprint. If you want low resistance and low shadowing, you need to go vertical, not laterally. And of course, vacuum depositing is also subtractive. We want 90+% transmission, so that means if we throw down a bunch of gold, we're gonna etch away 90+% of it, which is also very subtractive, very wasteful. So there are approaches to solve this, and figure there's we a network of some wire, and they're percolated, interconnecting, or we actually go to intentionally high resolution printed grids. And we touched on both those. We developed slot die coated nanowire composite films. So one of the nanowires are readily synthesizable and makeable, and they work. They work actually pretty well, surprisingly well. There's many recipes out there, but the fundamental problem with nanowires is roughness. So these little wires are in the tank, but you have one of those wires pointing up at an angle through a film, and you have a short, or at least a micro short, and that can yield killer. And there's like we encapsulate it in PEDOT. See, but we're lead and oxide. This is probably tin oxide, tin oxide. Embed those in the go past coating. It's a continuous solution of PEDOT continuously, and get some quite good results versus ITO. And this is all done very low temperature, 70 degrees C max drying, and you could probably develop it lower than that. This is a plot here. I'm showing typical stuff out there. Everyone but CNT, or merit of CNT in terms of cheap resistance and transmittance. Here's the IT. We want 10 below 20 ohms per square and about 90%, and that is the ITO range. With these silver nanowires, we show we can actually but at very low temperature. So the good news about that is that now we could go on plastic substrates. We could even potentially go on top of perovskite. but we're still having issues with yield. There's still questions about the roughness of that. And there's some strategies, but fundamentally that's an unstable system when you have these wires sticking out everywhere. So we looked at what we do well in the rest of our work in our lab, which is in ultra high resolution printing. And so we did some modeling simulation to show that combinations of a printed grid plus a relatively mildly doped high sheet resistance transport layer can actually achieve very, very attractive figures of merit. So this is the example, 1% power loss from sheet resistance. Remember, we're talking about 10 to 15%, even from, this is much lower than the power loss from the sheet resistance of ITO. And these are all scaled to 90% transmission, all the data here. And for example, say an antimony tin oxide, 5 kilo per square, very mildly doped, we actually doped transport layer get this to this 1% power loss from sheet resistance, and it's possible. Of course, this is all hand waving possible. So how do we make that a reality? So one of our specialties in our lab is printed electronics broadly. And of course, I've spent plenty of time working on sort of conventional flexographic printing or Revere printing, conventional inkjet drop is say 10 picoliter, and maybe you can get 1 picoliter, but that's somewhere between 50 and 10 microns of effective printed line width because the drop is going to. And by scale, we're now working with electrohydrodynamic inkjet, where we use extremely high electric fields to kind of break through the surface energy barrier for very small drops. We can actually produce submicron particles that come from drops. We can pull drops out of the head that are a femtoliter. So 1,000 to 10 than sort of conventional. And so we can prevent these extremely fine line widths. That's really interesting for printed electronics broadly to get into high performance transistors, sensors, all that. But it's also really interesting as we want to get, if we look at some of the grids, the finer we can make the grid, the higher light and electron transport layer, basically. And so this is very attractive and it's also it becomes essentially invisible as well. It's essentially transparent to the eye. You can't see these lines at these sort of sizes. So, and we've been working on this process. Electrohydrodynamic inkjet's been around for a while, but it hasn't really been a well-developed manufacturable technique, and it's only been demonstrated in some kind of very specialized materials. Work directly with SI technology tools, and we actually we're the world's first multi-nozzle roll-to-roll system. So a monolithic multi-nozzle plate like you would see in the inkjet and Epson on your desktop, where you could have hundreds or even thousands of nozzles in a head. And that's critical for this. Why? Because the great news is we're printing a micron at a time. The bad news is we're printing a micron at a time. It takes a long time to make a centimeter out of a micron, unless you can print a lot in parallel. And so the idea for conductors and inkjet are simple electrodes. We essentially need an array of single nozzles blasting away at the right pitch, continuously depositing lines to make our transparent conductors. So we're demonstrating that for the first time in a roll-to-roll. And this example of these you can see we have some limitations we have to do, but transparencies 96, and that's a combination of printed grid plus, in this case, a PDOT PSS, but heavily doped PDOT. This is like OLED grade PDOT. I can't remember the resistivity, but PDOT. This is the HTL or whole vection layer type OLED, which is relatively low conductivity, high resistivity. And with that, 10 per square meter on that. So pretty promising stuff. So it's all about. And this is an example of that. This is the print from SJ. We've been developing this. Actually, it's a lot of lines, and these are probably about 7 to 10 microns in particular, continuously printed in one to produce this sort of resolution. So pretty promising. And so watch the space. We also use this to print. I'll mention some of the other materials. We also use this to develop photonic and quantum materials. And example of printed metasurface using different phase shifts is the lensing part is total about 500 nanometers thick, and it can have focal length as short as 10, 15 microns, but certainly millimeter focal length is this lens, 500 nanometers focusing stuff at 1 micron, laser 1 micron, ultra flat. So you think about ultra flat solar micro concentrators, things like that. It's very, very interesting. That this is really tuned for 5 micron. This is tuned for infrared. We're obviously going to push that to ability pattern. And this is all functional materials. This is not two photon conversion, special photopolymers that are interesting but not actually functional. The high titanium dioxide, even down to submicron sizes. Pretty. Other applications we're looking at perovskite. So I think the U.S. map broadly, we always talk PV, but actually perovskites is a whole semiconductor area. But also things like piezoelectric. It's like hybrid perovskite, low temperature solution process. We deposit on, sub 70 degrees C, slot die coated. Solution process. It's relatively accurate material. It actually has, just like the old perovskites, they have huge dielectric properties, huge polarizations, electric polarizations, polarization axes, which is important for polycrystalline film. If we're going to print this from polycrystalline, if we have many different polarization axes in the materials, we get strong from different polarization axes. In a crystalline film, we're very likely to have a grain polarized in the direction we need to get our polarized device. So we developed this concept, developed the inks, and also developed a test structure for this. This is based on that ultra high resolution metal print slot die coating of this piezoelectric perovskite to produce fully printed flexible perovskite vibration sensors. This would detect, like say, missing rivets on an airplane wing or bullet holes in a fighter jet or something like that. We could actually pick up and even directionally identify the direction from which a vibration is coming with the correct sort of array of sensors. Here are technically probably the hard part here. Get this thing stuck to the surface and measure the. And this is inkjet printed our first demo of this in an actual sensor. We see the response sensor. When we go resolution 50 micron IDEs, we reduce the almost an order of magnitude. So a very promising area, kind of expanding on the palette of what we can do with these novel perovskites. Last, I'll wrap up and talk about the resources we have for everyone to access this. I tend to be very open in my presentations. I don't hide a lot of stuff because, here, part of the reason I came to University of Washington was to make an impact through the Washington Clean Energy Test Beds and providing open access resources to academia, government, and industrial users. And we have probably over 450, maybe 500 users at the lab in total. We're recovering from COVID. We are actually fully operational. Now we're actually matching and exceeding the pre-COVID usage of the lab. So we're super excited. And really the key is a couple things. We have world-class equipment provided generously by the state of Washington. We have world-class staff, and we have a really great working model where we can engage through normal funded research, like a DOE funded project, like the ones we're negotiating now, all the way, or you can actually contract us to do work for you. You can have our staff do work, or you can actually get trained on our equipment, and we're a 24/7 operation, access the lab at any time. Either of those last two, if you're paying to use the equipment, which is heavily subsidized. The equipment is free. We're only charging to recoup the operating cost of the equipment. You maintain 100% IP ownership of anything generated. So it makes it a very, unique university environment that there's essentially no university claims on any of the intellectual property, and very attractive for companies. And we probably have about, of that 400 or 500 people, users, we probably have 50 companies, and they range from, as big as Microsoft down to, Blue Dot or companies that don't even have a name yet. It might be one person using our lab. We have the full spectrum, and they go from early concept tests all the way to, we do pilot scale manufacturing for membrane companies in filtration and batteries, doing, hundreds of meters, kilometer sort of scale stuff. So we do all that within our lab. There's the scale up system integration, we simulate integration. We also have research and training. Of course, the big attraction and undeniable, no coincidence, the focus, advanced manufacturing or roll-to-roll is a big component of the lab, the roll-to-roll stuff. Also have flatbed coders, screen printing, we have 3D typing systems, 2-photon prototyping 3D printers, and a full suite of support equipment for measuring film, ink properties, all the way through to electrical properties and full devices and full module testing. And we can do full damp heat, full scale damp heat tests and full flash tests of 2-meter modules. And it's really the other secret sauce I think I already mentioned is really the staff. Getting all these tools together in one place and getting the professional staff that can get you operational, keep the stuff working, and get you what you need as soon as possible has been, I think, really, really effective for us and the people who've used our lab. And it's open access. We have people come from Israel. We have people who come from, Bellevue, Washington, across the lake. We have, a really diverse user base, and we're always looking to grow it. I mean, it's our goal this is how we're going to push the adoption and the spread of adoption of more rapid adoption of clean energy technologies by doing this. In a very open and accessible way. And again, I just want to say we have stuff here. And this is a real perovskite coming off our line. These are you can see on the right, and these are very photogenic, but probably I would say 1% of the time are we doing this printer, because in an hour this printer, a month worth to look at. But we also do a lot. Probably 5% happens on flatbed, which can be on flex, it can be on plate glass, it can be on silicon wafers, it can be on anything. So we don't just do roll-to-roll. And in fact, we predominantly do other stuff as either the end game. This is certainly the end game for many people. They're perfectly happy to work on plates, or the feed to the roll. And the systems, the coding systems we use are identical. More than identical, they're the same thing. We can 100 millimeter. We can go to 300 millimeter wide. That die head goes onto the roll-to-roll system as well. So you can literally, and the full ink delivery system, the whole thing, you can literally pick up, take it off the flatbed coder when you're ready, and move it to the roll-to-roll. And nothing has changed. It's the same head with the same liquid in it. So trying to get a really good transferability of technology. This isn't meant to be an eye chart, just for future reference. We have the point here is we have lots of deposition tools. We also have a lot of characterization to support it, and it's all under one roof. You don't need to go off to Charles Evans or go send it across the country to get a result. You literally 90 seconds. You can walk over to an instrument and get the feedback you need. Get the surface morphology, get the composition, X-ray, whatever, and then within minutes of encapsulating your device, you can go and test it too. We have, AAA plus testers for DC testers for cell test. We have EQE systems that will go up to, I think, 12-inch mapping EQE systems. And then we also go to full scale flash testing of modules and huge environmental chambers, walk-in environmental chambers for testing banks of modules. So we really kind of keep all this under one roof. So that's really about fast feedback. You can iterate fast. You can do maybe experiment in an hours that could take you weeks if you had to do this, accessing different pieces of equipment across campus or at different locations. We also, another important component, and headed up by a close colleague, David Ginger, which many of you know, is the research and training test bed. That's also part of the test beds, is also accessible to external people. It's actually on campus and has a student focus, but it has world-class tools, medalists across staff, and film deposition and test, catalysis, nanoparticle, battery cooling cells, sorts of characterization. We run a really special course in 1 quarter, really 12 weeks. We run through 5 different lab modules where people build PV cells from scratch. They build battery cathodes. They do a grid simulation, 5 different modules, hands-on in 1 quarter. And Dave Ginger really headed that up and has made that a reality in our lab. We also have other facilities on campus. An example, this interesting perovskite scanning probe microscopy in the MAF, which is the molecular analysis facility, also an open access, industrial accessible facility. Everything from photo mapping the TIR, the tunable infrared, to large scale mapping, to new things like the Cypher, which is environmentally sealed, high video rate imaging and light, so we can do sort of time dependent maps. It's video, very high speed AFM with, and we can build experiments and actually look at and that involves lots and lots of AFM scans, which means huge quantities of data. So sort of, but this has the computational support those huge blocks of video data, time, 4-dimensional data, and analyzing perovskite and other films. So with that, want to give good time for questions, and of course want to acknowledge the Department of Energy for the work you saw, but especially support from Clean Energy Institute, which we're a part of, the Washington Research Foundation, which really brought the roll-to-roll capability to our lab, and the state of Washington, which has supported the development of the clean energy test beds as this open access resource. So I hope I touched on something interesting for everybody, but I'll leave it to Joe to handle Q&A.
If I wasn't already at NREL, I know where I'd want to go for graduate school for sure.
We got a spot for you. I got a desk for you.
maybe there's still time. But I hear the academic standards are quite high there, so
It's crazy. It is crazy. I'm just going to rant on that because we have direct to college admissions. The new standards. We're the major research university in the state of Washington, which is a pretty high tech area, and the quality of students. I mean, I don't know. Like, I went to a pretty good undergraduate school. I don't know how well I'm doing it tough. It's tough. The students are the standard of students entering now is so competitive for the state universities. I'm sure everyone sees that around the country. It's really, really impressive.
All right. So there's a couple questions, and actually I have a couple written down too. The first question was actually with respect to some of the thin glass work that you're doing with Corning. And the question was, has anybody done anything like hail impact testing with flexible glass that you're aware of?
Yeah, Corning does. Easy way. So that's a good question. And I think so there's impact sensitivity, especially, but a lot of it is extrinsic. So, for example, even when we do the roll-to-roll, it's a statistical issue. Like, we can run for a very long time at tighter than 4-inch circumference, kind of exceeding that. But then there's some defect, there's some edge defect, and you get a total failure. And that edge defect might have failed. And I think it's the same for the impact testing. So it's statistical. There are people, they laminate. One of the options is to laminate to also like a polyester or something to provide better impact resistance too. So that's an angle that I've seen done, not within our project, but previously, before there was Willow Glass, there were other players in this space as well, and Vitraflex and a few other people were doing that to good effect. It's a good question. Corning has that data. Sean Garner, which some of you will know, is super. Everyone at Corning's great. Sean's super expert in that. Reach out to him, and he knows a lot about plexiglass, a lot more than I do. But there is definitely impact testing data. It's not something that we do.
Okay, fair enough.
But obviously, we've got to worry about hail.
All right, so there was another question that's actually got a couple different parts to it. The question was related to what you would consider the most important step to have humidity control for. Is it really in the drying, crystallization, crystal growth, or even say the initial kind of wettability and printing?
Probably a good question. I mean, there's a lot of different recipes. I glossed over that. I mean, we looked at one-step process, the original kind of early stage one-step processes. We've looked at like the NREL process, and I want to attribute it right, but Dave Morikazu, doing the sort of acetonitrile methylamine kind of approach. You guys had a great paper a little while back. That's a single step. So there's a lot of different recipes, but certainly at the point of deposition, it's really can have dramatic impact. You see that grain size exploding and moving around, in surprising ways. There is a just right. There is a minimum in that curve. Like there's strange functionality. It depends on the different recipes, but definitely at the point of deposition is a huge factor. Some of these new recipes, one of my biggest concerns getting into this was actually thermal processing. It had devs love that. Because it used, in OLEDs, you have to bake an electrode. For people, I just put it in the oven overnight. I put it in the oven for an hour. Well, if you're working at a meter per second, an hour is 3.6 kilometer long oven. It's crazy. So the early reports from process were troubling because people were throwing it in the vacuum for hours and stuff. That's really become much less of an issue now. And there are even the recipes where almost no thermal processing with some of these co-solvent approaches, excess methylamine approaches. So definitely the point of use, it depends on the recipe, whether it's that important in the actual thermal processing, but that thermal processing is less important. In general, it's pretty easy for us to purge the ovens in any case, because at that point, the film is not really liquid anymore. So we don't have to worry about fluid entrainment and stuff like that with the gas stream. So I really worry about it at the point of use. There's some possibility in the ovens, but some of the recipes, that's not an issue because there's hardly any time in the oven. It's only tens of seconds, minute or two.
And so I'll take a point of privilege since we only have one more minute left in our time, because it's been a really fabulous talk. I guess I was very curious if, in the context of some of your line printing, right? If you look at subsequent coating, I mean, have you looked at essentially cross coating versus inline coating? That is to say, parallel to your direct write lines, and does that impact some of the perovskite properties? So that's question part one, and then question part two is: have you tried direct writing actually some of the perovskite precursors as well with the I guess it's the electrohydrodynamic inkjet?
We've so the last one's easy to answer. So we've looked a little bit. So the electrohydrodynamic is kind of like a really high finesse electrospray. And you can actually run it in spray mode. So you can actually kind of use it as a very high resistance spray coater. So we've done that. And the other thing about the electrohydrodynamic is actually it has a wide parameter space in terms of viscosities. You can put water all the way to almost a viscosity like 1,000 CP through it, which is unheard of. So you can spray coat and coat we have not actually high resolution EHD printed perovskites, except, let's see, this one that I pushed through. Do I not have a picture? Well, we're doing, I think it got cut for time. We're doing like quantum materials handling. So we're using the hydrodynamic inkjet to put. We're trying to make couple single quantum dots to waveguides. People use
Okay.
stochastic approaches, but there's a huge amount of noise. They're just coding particles everywhere. Oh, look, there's one next to a waveguide. Let's look at that waveguide. We're actually going, let's place a nanocrystal on a waveguide. And in that case, we're actually also doing perovskite nanocrystals.
Oh,
So
very
we've
cool.
done quite a bit with that. So we're actually putting, the ultimate is to get to homeopathic solutions where we're literally, can we put a perovskite nanocrystal on a waveguide, plus or minus like 400 nanometer waveguide or something like that. I have some great pictures. So the answer is yes. So definitely inkjet EHD printed perovskite nanocrystals. But we haven't done the high resolution of this because I'm sure there's some interesting transistor structures and stuff you could do with it, but in the slower space, I haven't looked at it. We are very interested in the other thing I think you're insinuating, looking at one of the other really interesting structures we could potentially make is an all backside contact cell. Super interesting for perovskites for many reasons, but one is because nothing goes on top. So you don't have to worry about any of this, and we can have huge grains because topography doesn't really matter because we're not going to have shorting through the film because all the contacts are on the back. And so we're looking at depositing perovskite onto pre-existing printed features. And it's early days, but yeah, you can definitely get texturing related to stuff. I don't know if you're saying it's nucleating, where it's nucleating from. Was it nucleate in the middle or is it nucleate from the fingers? But you can definitely get textured growth related to the underlying structure.
Very cool. Well, excellent. This has been a wonderful presentation. Devin, thanks so much. Again, I'm dying for travel restrictions to be over so that they'll let us come out and visit you guys again, and maybe I'll get some actually hands-on time in the lab. Would be awesome.
Great. And everyone's welcome, but Joe especially so.
With that, I want to thank all our attendees, and next month we have Gang from First Solar who will be presenting at our USMAP seminar, and you should check out. We'll have the information about that webinar in the not too distant future. So with that, I'll thank everybody again, and especially Devin, and best to everybody.